Hi, everybody. Thanks for coming. Really appreciate you spending the time to get interested in SPEE, and really keen to tell you where we're at. So welcome to this webinar, From Concept to Combat. It's great to be here.
So, g'day guys, my name's Matthew Harbidge. I'm the Technology Product Manager for SPEE3D. So, been here for quite a while. So most of the trials that we're going to be talking about today, I've been at, basically all of them except for one. So generally as the engineer on the ground, helping customers run the machine or just running our machine, solving the problems and dealing with the challenges that we get stuck with when we're on trials. So trials basically never go to plan. They have this big, beautiful plan and never survives first contact with the actual challenge. So we can talk about some of the challenges that we've had along the way and the ways that we've had to solve them, and then how our product differs afterwards because of it.
Yeah, so hi, my name's Matthew also, Matthew Turner. I'm the Principal Project Engineer here at SPEE. And yeah, I look after new product development and technology development, getting things that Matt said, distilling them into how we can implement into our product, and then manufacturing a better product. So move on. So we're going to run through these trials and give you a taste of what environmental conditions these were put under, how we define success in the trial, and then what were our lessons learned, what were some interesting things, and then how did that affect our product. So like we said before, we've got our formative trials in Australia, the desert. Trial by ice, where we're talking about going to polar opposite conditions, cold weather, point of need challenge, and also living the dream in Hawaii. So now we're talking about salty, hot conditions and the first deployment of a full EMU system. Also continuous improvement on our technology, what's next in our materials and geometry. Also, title of this page, why is it red?
And how do we say speed?
Yeah. All right, I'll hand over.
Excellent. Let's get into it. So our first lot of trials working with basically an Expeditionary product were in 2020. So if you might remember, it was a while ago. The whole world was basically locked down due to COVID. I was based in Darwin at the time, where I'm originally from, and we basically had the Australian Army reach out to us and ask us to go on a trial with the Warp Speed product that we had at the time. So in this time for Speed, we had two different products. We had a Light Speed, which is our smaller base machine, and Warp Speed, which is the larger machine you can see in the picture. So these machines were designed to be run in labs or in factories, and basically that's what all of our customers did at that time, right? So they were universities, they were print bureaus, or they were early adopters. So we had zero experience running an Expeditionary capability, and we didn't really know how the machine was going to go. So we knew it wasn't waterproof. We knew what it could do in the lab, and
lots of lab experiments.
Yeah, so being able to put it outside under the sun, under the stars, was definitely a big change. So it was a lot of learning that we were about to enjoy. So we did 3 trials with the Australian Army over 2 years. So those first trials were basically just taking the machine out into the field, seeing how it transported, can it actually print parts in the field, how do we handle powder, setting up all the equipment, checking after transport.
How do you deal with it being bright red?
How do we deal with it being bright red? So of course the first machine was bright red. All of our machines up until this stage were bright red. We're speed, right? We're fast. Red is the fastest color. So that was a contentious issue for the first trial, is everyone asking us, why have we got this giant red box in the middle of the Australian bush? Which once has been quickly rectified, as you see in this other picture, where they spray painted in camo. Beautiful paint job. So the second trial, we introduced a small CNC machine, some heat treatment capability, and that's kind of the first time we were running the capability from start to finish, solving problems in the field and producing and validating parts that could be put into use. And then our third and final trial with the Australian Army, we had a prototype of what we call Speed Cell, which is a containerized CNC and heat treatment capability. So part testing, a nice space to be able to draw the parts as well out of the elements. So that was a product that we developed over these years working with the Australian Army, as well as the printer product that we developed as well, which Matt will talk about in a sec. But basically for these trials, success was defined as, can the Australian Army use these products to solve the problems that they have in the field? So whether that's they need to make custom parts, make replacement parts, specialty tools, being able to produce and procure these things away from base when you might not have enough spares, or you've broken something weird that you don't normally have to replace. So being able to maintain your readiness with your various capabilities away from home. And so to that end, all of the trials that we did were really successful. We went from a product that was a factory-based thing to making it work in the field.
Yeah, you really describe these formative trials exactly that. You know, it's validating the product, and it's also inventing something, isn't it? Like we talk about like that spanner you see there. People lose those all the time, and the idea when you're on a trial, you want to keep more kit in the field as much as possible. And a lot of that is keeping spares. You've got to predict the future. What are you going to need that you're going to lose or break? And often that can be wrong. And it's no expense spared to keep that kit in the field. Whereas these trials showed that the real value of this is that if you've got powder, you've got people, you can and power, you've got parts in the field, and that's any part. You don't have to predict the future. You've got the kit on site. So this is a beautiful use of minimum viable product. So there's 3 trials. The first one is the machine in the field. Second one, let's change the color. It stands out looking like a sore thumb. And then the third one, let's get more functionality in there. And that brings us to, I guess, the EMU. What does EMU stand for again, Matt?
So Expeditionary Manufacturing Unit.
So I can talk a bit about getting all that learning and just putting it into this product. So what we see here is the current level final version of the EMU products. So there's a huge amount of integration, design, and ruggedization development put into this. Just focusing mainly around integration. So we understand that the warp speed core technology worked and it's viable. So now it was about, how can we improve things like deployment and get that quicker? And it's really loud. How can we make it quieter? So on the right there, we've got a logistics solution, which is our shipping container shape. And we have brought on board the auxiliary equipment to get it running. So from our powder feeder, compressor, dust extractor, and electrical system, bringing that all on board so we can, deploy it quickly. Also, the added advantage here is making it quieter. Putting it in this box, we can bring the noise down 10 dB, and it's quite comfortable to operate around. Other things to talk about. We've got a more durable robot bag. We've got better usability of the build chamber, and one of the cool things is the robot pose. So when it's finished, we've got the weighted robot pose where it prints the part, and when it's finished, it'll present it to you. So it's easy to take off the substrate holder. The other cool thing was that Matt's got a cool story about, I guess, it's the navigation pad. So we had a touch screen, but that didn't quite work for us, so we integrated this thumb navigation pad. Do you want to tell us a bit more about that?
Yeah, sure. So on one of the trials that we had with the Australian Army, obviously we've got this warp speed in the field. The interface for a warp speed is a large touchscreen panel, right? So it's big, it's beautiful. You can see it from across the room, but it's not really meant to be outside, right? So it's not ready for being directly exposed to sunlight. It gets really, really hot. It's not really bright enough to see in full sunlight as well. And at nighttime, of course, because it's a big bright light, it attracts bugs. So we've got moths and other sorts of little creepy crawlies from Northern Australia walking across this thing, pushing buttons effectively on the machine. So we had like literal bug problems at night when we're running a warp speed. So there was a good bit of time where we're holding a piece of cardboard over the HMI to stop bugs from pushing it. So the change that we made on XSpeed, of course, for improving ruggedization and deployability is we've now got the HMI panel is rated to be full sun, really high temperature conditions. You can read it in full sun, and we've got a touch navigation on that now, so we don't have to worry about bugs crawling across the screen anymore.
Cool. So that's sort of XSpeed on the right there. On the left, we've also got the speed cell. So part of the EMU is we print the part and then we need to post treat the part. So do you want to tell us a bit more about the prototype you had in the Hampshire?
Yeah, so the actual prototype speed cell that we had was on the third trial. So we had a CNC machine. We've basically kept the modern version of that CNC machine in our speed cell product. And we've got 2 large furnaces. Before we had 2 small furnaces. We didn't really have any insulation in the original prototype, no air conditioning. So they're all things that we've changed. So at the time, it did the bare minimum, right? We could heat treat, we could machine, we had a space to test and a space to draw. But it was really hard, it wasn't particularly comfortable, and we couldn't process the size of parts that people need and that our machines capable of making. Yeah,
so that, I guess then for us, the design update or the design side here, we're looking at comfort. Number one, you've got to be in this for extended periods of time. We want that air conditioning, we want the insulation, we need it. So it's a nicer environment to be inside. And also on the left there, we've got some big ovens, and there's 2 ovens there. Matt, why do we have 2?
Yeah, so there's two different types of ovens in this case. So the one on the left you can see, they're actually both about the same size on the inside. The one on the left is the lower temperature unit, it's rated for about 650. The one on the right is the high temperature one, rated for about 1200 C. So they're made for different parts of the heat treatment. So depending on the type of material that you're printing, you need to cook it at a different temperature for a different time. So having 2 of them in there meant that we could do things in parallel. We could heat treat 2 different materials at the same time. We could basically take things off the critical path, right? If you're cooking bronze, which is a reasonably long heat treatment, but you've got some parts you could be making aluminium, you can print them on the XSpeed and then heat treat them in the other furnace.
Yeah, takes it off the path.
Yeah.
Very cool. All right. We'll move to the trial. So now we've got a trial by ice. So we've been in hot conditions and we've developed a new product, and it's now ready to be trialed. So in December 2023, the US Department of Defense awarded us the Point of Challenge cold trial. So it was the first trial by ice that XSpeed will experience. So this is just the XSpeed product at this point, not speed cell. It's in Hanover, New Hampshire, and it really was to see what sub-freezing conditions had on the printer itself and on the parts that we print. So quite simple, really, and it would be the first of its kind. So, as to our knowledge, there isn't 3D printing in sub-zero conditions. So this was the rough spec was to bring it down to -20 degrees. So the printer would be fully freezing, so saturated at -20 degrees. Then bring it quickly or slowly or up to 20 degrees, so lab temperatures, and then print. So that would be done in New Hampshire. We'd bring it into a cold chamber, bring the temperature down, then put it in a heated room and bring it up to 20 degrees. So in the true spirit of trials, nothing ever goes to plan. And day 1, the printer was late. So the printer was just in time, built and shipped to the US. And day 1, it hadn't arrived, which actually turned into a bit of an advantage, and we could actually get the place prepared and get prepared for the printer coming in. So pretty quickly, we saw that we didn't have the ability to bring the XSpeed up to temperature, up to 20 degrees, and that we'd have to print in -20 degrees conditions. So day one, planet. Day two, the printer arrived and we had to start defrosting critical parts of the printer. So we're talking electronics, electronic drive, so that the motor drive for the compressor and the dust extractor, the robot controller as well. So, and the compressor itself. So really putting space heaters pointing at these devices. So they were all frozen solid. So the other thing to note was we have a cooling system for our core technology. In Australia, we use a coolant. So it's just to stop corrosion. Despite our best efforts of removing that coolant, it still froze solid. So we had to defrost the chillers and source a glycol that doesn't freeze. So that's something, we're coming from really hot conditions here. It really gets cold, and really quickly learning. So day one, defrosting, day two, defrosting. Day three, we needed to power up, but we needed to continue defrosting. So the compressor still wasn't happy, still wasn't up to temperature. So we just a bit more defrosting and then we're able to power up. So powered up and we need to keep defrosting. So the build chamber is at -10 degrees Celsius, and that's too cold for the robot. We want to de-risk it. We don't want the robot to mechanically fail at -10 degrees. So what we're able to do is just run it at operating temperature, bring that the build chamber up to 10 degrees Celsius, and now we're ready to print. So you want to tell us a bit more about what we printed?
Yeah, sure. So the definition for success for this particular trial was being able to print in these conditions. So as you said, we wanted to basically store it really cold, warm it up to some nice conditions, and just see if it printed. It didn't go like that, so we ended up having to set ourselves a higher goal, which was be able to print in actual freezing conditions, so -10 to -20. And what we wanted to know is whether or not the parts perform the same in those below zero conditions as they would in ambient conditions. So we printed a whole bunch of samples that were mechanical testing samples, as well as a few case study type items that you can see, like for example, our colleague Savan holding the big copper spanner, copper wrench. So along with the tensiles, we produced some in these freezing conditions, and we produced some in the ambient conditions as well. And we rate those set of samples, right? So we compare how the machine performed in each of those conditions. And in both cases, they were nice and close together. And more importantly, they exceeded the data sheet values that we saved for that material. So that was basically ticking an unwanted stretch goal, as well as ticking the goal of finding what the impact of the environment was on part performance.
Yeah, really exciting. So now, great success. We're able to get over the line. So now we've got some more knowledge about what our product needs to be. So my key takeaways here, what we did was put in a compressor sump pump heater. So this is not an uncommon thing to do, and also integrate that into our system so the user doesn't have to think about it. So the compressor now has a heater on board that when the machine powers up, if the compressor is below a certain temperature, the compressor will not start and it will just pour heat into it. Bring the compressor up to temperature and then automatically operate. So the user really doesn't have to worry about the temperature. It will just work. Also along that line, we've got heaters inside our pneumatic valves, which also automatically operate when needed. What else? Some really easy things to fix was we've got an air cooling system in our auxiliary side, which was basically set to on all the time. So really we were trying to cool with air when we didn't need to, something that we love in Australia. So this is cooling people as well. We have it on all the time. That's a very easy software change where if we're below freezing, we don't need our cooling fans on. Also some simple usability changes. So, we've got a flat floor in the build chamber. flat floor now in the build chamber, which is so it's easy to step inside, make changes to the nozzle, or maintain the nozzle as needed. Okay, I think that's enough on the ice trial by ice. Move to the next trial, which is Living the Dream in Hawaii.
Just briefly on the trial by ice for anyone who's watching, there's a really good YouTube video on our channel, which it's about 5 minutes long. It goes into detail about that whole trial, which is pretty cool. So cheers, Matt. So Living the Dream in Hawaii, this is another one of the trials that I was on. So in the trials we've talked about so far, we've done hot and humid, dusty in the Australian outback. Effectively, we've done cold trials. We did a couple of other trials in the desert and at Fort Irwin and things like that. But this is my first time in an actually like really pleasant place doing a trial. So Hawaii, just like the postcards, is beautiful. The weather's really nice to be around. The first week that we were there, we had a lot of rain. So proper tropical rain that you'd expect. But otherwise, temperature-wise, really, really quite nice. The other sort of important milestone for this trial for myself is this is my first time seeing the full emu in the field. So the speed cell that we've got here and also the X-Speed. One of our other customers actually had the same capability as well. They were deploying about the same time. So we're seeing sort of both of these capabilities get deployed around the world and learning at the same time. So for this actual trial, our customer, Naval Postgraduate School, so they're the guys who own the X-Speed. They were invited by the US Navy to come to Hawaii and do this particular trial. So what the task was to repair battle damage or get a ship ready to be underway after sustaining damage. So the ship in question, you can see in the background now, it's the USS Tarawa. Now, unfortunately, on the bottom of the ocean, but that's how trials go. Not our fault, that one. So we were there supporting the Naval Postgraduate School to run their X-Speed, helping them run their X-Speed to solve these problems in the field. So we've designed these two products in mind that we call EMU together, so that you can solve problems that come across your plate, right? So someone comes in, they've got a problem, it's a broken flange, it's a dinged in valve, completely destroyed valve, bracketry, things like that. If you've got a problem you need to solve, so we can do the design, we can do the printing, we can do the heat treatment, we can do the machining, and also do the part testing in the field, right? So this full expeditionary capability. So a lovely picture on the right-hand side there of one of the guys from NPS doing a heat treatment. So that's a bronze pipe flange that we'd made. So that ended up being welded onto a big pipe that it sustained, simulated battle damage in this particular exercise. So the goal that we wanted to demonstrate for defining success in this case was, are we able to use this capability to solve parts in the field? So we made a bunch of different parts in the field from a few different types of materials. Some of them we were welding onto other existing parts. Some of them just replaced existing parts. Working with the other vendors there as well. So some other people were showing off their machining capabilities, welding capabilities. Was a really good experience all around. But generally, just trying to prove that when we've got this capability, people, powder, and power, that we can make parts.
Yeah. So then, this is the same X-Speed design that was in the cold trial. It's a different product, but different machine, but the same product. And this is the first time we're using the speed cell product here as well. So our takeaways on the speed cell, really, it was pretty simple. We were able to optimize this space so we can get more stuff inside and a better air conditioner. But essentially, there wasn't some huge changes. It was more a quality build and really getting in more validation tools. So getting the right hand tools inside there so you can validate your part as well. But the huge takeaway here, I guess, was the materials and the blended materials that you were using.
Yeah. So the materials that we had on the trial were a type of aluminium bronze. So that's what you call binary bronze. It's just a mixture of copper and aluminium. We had 661 aluminium and 316 stainless steel. So that's great. And the parts that we made, we're able to test, and they were fit for purpose. So, but really what the DoD prefer, US Navy, and lots of other customers prefer is they want to be able to replace parts with a like for like, right? So in this case, these guys are generally really keen on having nickel, aluminum, bronze, for example, copper and nickel. So the pipe flange that we're replacing in there is normally made from copper and nickel. And really, even though we were able to test it and say, yeah, cool, this thing is fit for purpose, they'd like to replace it like for like. That way they don't have to worry about long-term issues of, we're going to have galvanic corrosion problems because we made the wrong material selection, even though it was mechanically fine at the time. So it just makes the whole thing a bit simpler to have the actual materials that they prefer in these types of applications.
Yeah, great. All right, I'll move on. We can move to exciting slide where, so now I'm going to conclude on, I guess, continuous tech improvement. So we've talked a lot about the product, evolving the product itself. And here's where we can just talk a bit more about our technology, improving it, regarding materials and geometry.
Yeah, so one of the ways that you can think about 3D printers, but also other types of manufacturing equipment is the solution space that they address. So these manufacturing capabilities, they've got to make materials that have certain properties, right? And those properties are the useful things that we want parts there. They're this strong, or they're this flexible, or they're fine at high temperature. And then there's also the part geometry, what shape it is, what type of shapes you can do, how big that thing is. So if you could do infinite things, then you've got effectively infinite solution space, which is beautiful, can solve any problem, like a Star Trek replicator. Now, unfortunately, basically every 3D printer I've seen is not yet a Star Trek replicator. So one of the things that we do is we're always trying to continuously improve the solution space that our machines address by offering stronger materials or better corrosion resistance, the common chemical like alloy systems that people are really comfortable dealing with as well. So the example we've got up on the screen has got two different materials there. One of them we launched a couple months ago that's called XNAB, or Expeditionary Nickel Aluminium Bronze. So this is a material that was designed, so it's a blend of a few different types of powder. We've designed so that you can print this thing in the field in air, so you don't need inert gas and nitrogen or helium. And you're also able to do the heat treatment fully in air as well in a speed cell. So being able to produce a strong nickel aluminum bronze, an alloy system that lots of people are really comfortable with in the field without having to carry around inert gases or worrying about running out of those things.
That's a really good point to how we enable, I guess, the expeditionary element of it. So typically cold spray, well, a lot of cold spray sprays with nitrogen. And we are focused with these expeditionary products on doing everything successfully with air. So it keeps the product simpler and hence more deployable. Moving to a nitrogen system in that sort of setup is difficult.
Yeah, you need to carry around a nitrogen generator, or you have to worry about your supply chain for replenishing nitrogen, and the machine eats a lot of air. So it's important for us to be able to keep doing these things in air. So the same for steel. So we've got a few different steel projects underway at the moment. So we've got some types of stainless steel, and we've got some types of conventional steel as well. The goal for some of them to be expeditionary, so being able to print them in air in the field. And then also some non-expeditionary ones where we have the flexibility of using nitrogen for high quality steel.
So the other thing that I've heard, and it's probably good to talk about, is that the NAB is potentially a good alternative for steel.
Yeah, so basically all the parts you come across in your life, the material that they're made from is basically a choice that someone's made at some stage. So whether or not that was easiest to source or easiest to manufacture, or it had the right mechanical properties for that part needed. So it was flexible enough, it was strong enough. So NAB is quite close to a bunch of types of steel in terms of its properties. It's generally a lot more corrosion resistant as well. So depending upon the applications that people have or don't need to be able to produce something in the field, NAB can be a really good solution, really good alternative to similar types of steel.
Yeah, as a designer, so not even coming from like repairing fields, it's good to know this, because typically we make a lot of decisions hereditary. We use steel because we've always used steel, but really what properties do we need that to be? And if we can print it, that'd be amazing, and XNAP can do it. So it really kind of opens up a designer's mind as well as to what we can do. So we can move on to the last point, which is sort of stepping away from the expeditionary side of things and just talking a little bit about the industry and commercial industry as well. So the obvious next step for us is big parts. So currently we have the limitation of a 40-kilogram part because of our robot. So we spray the part onto the robot, which limits us on weight. We can't really go above 40 kilos. So the obvious next architecture step update was to move the nozzle off from being static onto the robot. So we have a known mass on the robot and it doesn't change. And then printing the part on a substrate or a rotating substrate. So that, we have built 2 prototypes in the field now. So we have one here and one's at a customer. So it's very much an exciting field where we're looking at lots of different changes, and that has opened up a lot of other needs. So for instance, if you're thinking from 40-kilo part to maybe a 2-ton part, how long is that going to take to print? A month. So a month, we're going to print for a month. I've really got to, I'm imagining how many times I need to fill up that powder feeder. I need some sort of infinite powder feeder. So in the background here, we're developing powder feeders to address that new need that we've created with this large format printing. Also, while we've cracked open that development, we're looking at different performance capabilities of that powder feeder, or a higher pressure, multi-feeding, as well as the infinite feeding, which is pretty exciting. Watch this space sort of thing. So thinking about that month build, the other challenge is maybe we want to stop-start. We want to guarantee success of a print. So we've got to increase reliability of our products, and then we have, let's be honest and go, all right, maybe we need to stop-start, observe, modify, change the print as we go. So we've got that input, that functionality implemented into our software. Calling Thunder Lab.
Want to make it easy to recover. Say you've got a power outage, or you run out of powder, or any number of things, right? If you're halfway through a month's long build, you want to be able to easily recover from that. Otherwise, you just lost tons of material.
Yeah, so really exciting area here, and so much to talk about. But this is concluding our webinar today. So I'm really grateful to be able to present this to you guys. We're doing this really to show that we want to respond to you as a customer. So we really want to hear what you've got to say. We're ready to adapt our product to suit what you need. So let us know. Don't hesitate to reach out. So it's time to go to your questions.
Yeah, I think just on that other note though, like anything that you'd like to know more about, or things that you think we should be doing differently for the Expeditionary as well as the large format stuff, right? So with a few of those machines in the field now, we're looking at getting more in the field soon. But the machine needs to be right for what you guys need to do. So if you've got any weird problems you want us to solve, or things you want to work on, let us know.
Yeah.
Right. Hey, thank you so much. That was really insightful stuff. It's great to learn more about how SPEE's evolved over the years and what you've read through your trials.
Yeah, I think just on that other note though, like anything that you'd like to know more about, or things that you think we should be doing differently for the Expeditionary as well as the large format stuff, right? So with a few of those machines in the field now, we're looking at getting more in the field soon. But the machine needs to be right for what you guys need to do. So if you've got any weird problems you want us to solve, or things you want to work on, let us know.
Yeah.
Thanks, guys. It's been nice sharing the journey. It's been a really exciting journey for myself, seeing the product change from this big red box that shouldn't be outside to these big green boxes that are made to be outside.
Yeah.